Okay, we're going to elaborate a little bit on the last video. So we're given, in this case, an extension. Then we can form two sets. We can form the set of intermediate extensions, which I'm going to call sqrt. I don't like that sqrt. We're going to make it like that. And it's a set of all intermediate extensions. I'm going to write it like this. K subset M subset L, M intermediate. And then sqrt G is going to be the set of all subgroups of the Galois group of L over K. And we've just shown, what have we just shown? We've just shown that there are functions, just honest functions between sets. So star, or asterisk, I think is what we're using, asterisk, takes in a intermediate field and spits out a subgroup of the Galois group. So that's M goes to M star, or M asterisk, which is the Galois group of L over M. And then there is dagger, which is a function from the subgroups of the Galois group to the intermediate extensions, and that takes a Galois group, sorry, a subset of the Galois group, and spits out this H dagger, which is, I'm going to write it like this. It's the fixed field of L via the H action. So what's fixed by H? That's the L's and L. So H of L is L for all H and H. Now, a natural question arises. What happens when we compose them? And these are kind of crazy functions. But we could ask that question. What happens if we compose these maps? And that is where the Galois that's where the fundamental theorem of Galois theory comes in. So we want to know, when are these maps bijections? So more precisely, when are these functions? In fact, these are intimately related functions. So I'm going to say mutually inverse bijections. All right. So let's work out the Galois correspondence in a very specific example, and it's going to take us some machinery to figure out when they are bijections. And that's going to be what the remainder of the course is, determining when they're bijections, and how do you go about computing these guys. So let's do an example we started with, our motivating example. In our motivating example, we had the polynomial t squared, I think, minus 4t minus 5 over q. And this factored as t squared plus 1, t squared minus 5, or I might have done minus 2. I don't remember. I'm going to follow the example in the book, though. And so we had these roots, plus or minus I, plus or minus root 5. And we had elements of the Galois. We had worked out what we thought was the Galois group. So there, just as a quick reminder, the Galois group of Q adjoin I root 5 over Q was this set identity R, S, and T, where, again, I is the identity, R was negate I, S was negate root 5, and then T was, well, fix I. It fixes Sorry, it negates both of them. So t of I equals negative I, and t of root 5 is negative root 5. And in fact, t was just R composed S. That's all it was. And so that was our Galois group. And this group, let's call it G, so I don't have to keep writing that out. G is actually abstractly isomorphic to Z2 cross Z2 because we have two elements that are order 2. If we do R twice, we get the identity. You negate twice, you get back to the original thing. If we do S twice, we get the identity. And R composed S is actually the same as S composed R. They commute with each other. Okay? So this is take your powers of R and S that you have and send them to I and J. Since they're order 2, this is going to be just fine. It's a well-defined isomorphism. All right, so what are the subgroups here of Z2 cross Z2? This has subgroups. Well, there's sort of take the trivial group, which is just the identity, that's I, and then it's take the subgroup generated by R, and then it's take the subgroup generated by S, then it's take the subgroup generated by R composed S, that's sort of the diagonal Z2. Inside here, that's like 1, 1. If I do 1, 1 twice, I get to the identity. And then take the whole group. So there's 5 subgroups. Okay. Now let's work out what the corresponding fixed fields are. So what is I dagger? So what does the identity fix? The identity fixes everything, right? So I dagger, the identity fixes everything. Since the identity fixes everything, to figure out what the group generated by R is, what the fixed field is, we just need to look at the guys such that, the elements in Q adjoin I root 5 that R fixes, because if R fixes it, the identity will automatically fix it, and so it's fixed by every element of that group. But what does R fix? R negates I. R is a negate I function, and so it fixes anything with a root 5. So that's Q adjoin root 5, sort of naturally sitting as a subfield of that, of the large field. And what about I S dagger? Well, similarly, S is the negate root 5 guy. So what does it fix? It fixes Q adjoin I. What about T? Well, T appears to not fix anything, right? Because it's negate I and negate root 5. But if we multiply I and root 5, then T negates both of them. It introduces 2 negative signs. The two negative signs cancel each other. So this actually fixes Q adjoin I times root 5. And then what does the whole Galois group fix? The whole Galois group only fixes Q, because I have to be fixed by R, so I have to be in Q adjoin root 5. But we also have to be fixed by S, so we have to be in Q adjoin I. So we have to be in both of them. The intersection of both of these fields is Q, and T will certainly also fix Q. So the underlying fixed field here is Q. Okay. All right, so this is us working out the fixed fields in this example. Furthermore, the collection of all fixed fields is only this set. We only get these 5 fields that we've seen right now. And how do you prove that? Well, it's very tedious without using the fundamental theorem. You can do it by hands, but it's not. I don't think it's worth the effort. But you can see that. Why does it keep erasing that? Sorry, let me move this around. It can be done by hands without any abstract machinery. That you only get these fields. We're not going to do that though. And what do we learn here? Well, there's only 5 fields, and all of our fixed fields hits all of them, right? And there's only these 5 subgroups of the Galois group. There's the trivial group, there's the whole group, and then there's these groups generated by order 2 elements. So there's only 5 elements of G, and there's only 5 elements of F. So G here is what? G is the trivial group, the group generated by R, the group generated by S, the group generated by R compose S, and then the whole group. In this case, star and dagger are mutually inverse bijections. I know this video is a little bit long, but let me just say a little bit more. So we have Q adjoin I, we have Q adjoin root 5, we have Q adjoin I root 5, oops, I times root 5, and then we have Q adjoin I comma root 5. And then we have identity, which I'm going to write as 1 just to make it a little bit easier. We have the group generated by T, we have the group generated by R, we have the group generated by S, and we have the whole group. And what star is going to do is it's going to take in Q and spit out G. It's going to take in Q adjoin I and spit out the subgroup generated by S. It'll do that, and that. And then dagger on the other side, sorry, I'm not all that great at writing daggers, is going to undo it. So G is going to fix is only going to fix Q. That's going to fix Q. S, the group generated by S is going to fix Q adjoin I, and so forth. So this is what I mean when I say mutually inverse bijections. Whatever asterisk does, dagger undoes it. Whatever dagger does, asterisk undoes it. And let me also notice one more thing. In this picture, we get things like certainly the trivial group is a subgroup of the whole group, but what does the trivial group correspond to? The trivial group corresponds to Q adjoin I root 5. And what does the whole group correspond to? It corresponds to Q. And certainly we can't write the subset containment the other way, right? And so here we have that contravariance happening again, which means, again, for this class, it just means inclusion reversing. Okay, and that will be a common theme. The Galois correspondence is inclusion reversing. So we want to know, when is the Galois correspondence a bijection, and that's where the fundamental theorem comes in that we have to build up to.